This section's on derivatives of inverse circular functions, so looking at inverse sine, inverse cosine, and inverse tan. Now those functions are also sometimes called arc sine, arc cos, and arc tan. So if you ever do see that in an exam, just to remember, and I'll just put it up here, so arc tan is inverse tan, arc sine is inverse sine, and arc cos, which actually looks very odd, is inverse cos. I think that just says 1c. Alright, so they're the formula, the different forms you might see for your inverses, but for this section we're going to be looking at them just in the form that we've regularly seen, which is the inverses with the -1. So what we're looking at here is how to differentiate these functions, and the cool thing about this is it actually uses the techniques you used in 6b. So what I'm going to do, I'll just get rid of this and we'll actually look at a little bit of a proof. Now the proofs are actually in your textbook for all of these different functions. So for inverse sine, cos and tan, I'm just going to go through the proof for inverse sine so you can follow it through. And then what I would advise you to do is actually have a look at the proofs for inverse cosine and inverse tan and make sure you can follow those through. They're very similar and they're working. So what we're going to do is we've got our function and we're going to call that y. So our function is y, okay, and that is equal to inverse sine of x. So basically, instead of writing this f of x, we're just going to write y equals inverse sine of x. That's the deal, okay. Now to go and differentiate this is a bit of a pain because we don't know what to do with this inverse sine. So what we're going to do is actually take the inverse sine over to this side where it becomes just regular sine, sine of y, and we just leave x on this side. Now this is in a form that we can actually differentiate. So I'm just going to write diff each side. Now at this point you might be thinking, or how would I differentiate this? I'm actually going to do this with respect to y on each side, and the reason for that is it's easy for us to differentiate the sine then with the y, and then you'll see what's going to happen on this side is pretty neat because it links back to the previous exercise that you did. So we're just going to do d dy of each side. So we've got d dy of x, that would be dx dy, like that. Derivative of sine is cosine, so this is cos y, equals dx on dy. So therefore, dy dx equals 1 on cosine y. Now that's awesome, that's a really nice result for us, but you can see that doesn't look like this, and that's because we have a y still in here. We'd like to get this in terms of x. So what we do is we use a little trick at this point, which is to get a value here for cosine y in terms of x. So what we're going to do is link back to what we know, and we know this, sine y equals x. We have cos y, we also have sine y, so we're going to use the relationship that links those two together, which we know is our classic using sine squared. Now this time I'm just going to put a y in there. It's completely equivalent, but it's more useful to us because we actually have y's everywhere. So what I'll do is I'll just copy this over onto the next slide so we can see. Oops. Copy that over, drag it up. So now what we're going to do is we're going to actually use this result and try and do something with this cos y. So this result here actually implies that cos squared y equals 1 minus sine squared y. Now that means that cos of y equals plus or minus the square root of 1 minus sine squared y. Now what we have to do is consider a few things in the question here. The first one being that we know what sine of y is. Sine of y is x. So since sine y equals x, that means that we have cos y equals plus or minus the square root of 1 minus. We can replace this guy now. Instead of sine y squared, it is x squared. Okay. Now at this point we have to decide whether we're looking at the positive or the negative case. And what I'm going to do here is I'm going to just go back to the question that we were dealing with, which was an inverse sine question, y equals inverse sine of x. If we look at your formula sheet, so this is your special formula sheet, if you're dealing with inverse sine, your domain is between -1 and 1, and your range is between negative pi on 2 and pi on 2. So that means for our question, and I'll just write this up the top here in green, then we have x is between negative 1 and 1, and y is between negative pi on 2 and pi on 2. Okay, so if we think about bringing this result over now, we've got this answer here, okay, cos, and we look at cos, and we think, okay, y is between negative pi on 2 and pi on 2. You know that cos of pi on 2 or negative pi on 2 would actually be 0, and that's impossible because we have cos y on the bottom. So really, this actually implies that we have a slight change on our original range for y. It can go up to but not including the pi on 2's because now cos is actually underneath, it's a denominator. So that helps us to see what the sign is going to be. If we think about drawing that as a diagram, and I always encourage you to draw pictures, we're looking negative pi, which is here, all the way to pi on 2. So it's all this side. And on this side, you know that cosine is positive. So we're going to take the positive branch. So for this particular question then, we end up with cos y equals the positive branch, 1 minus x squared. So therefore, dy dx, which is what we were trying to find all along, which is 1 on cos y, is actually 1 on the square root of 1 minus x squared. So instead of being 1 over cos y, which was not helpful to us, we looked at the link between sine and cos. We already knew what sine was. We wanted to find cos y. We substituted sine y out with the x, and then found which branch cos y coincided with. So dy dx equals 1 on the square root of 1 minus x squared for y equals inverse sine of x. So that's actually the derivative of inverse sine. You can do similar arguments for inverse cosine and inverse tan, but I encourage you to have a look in your textbook and see if you can actually prove both those results yourself. One thing that I should say actually before you head off to do that is with this function too, remember that the denominator here has to be not only non-zero, but it also has to be bigger than 0. The reason for that is you can't have a square root of a negative number. Well, we know that we can, but because we know complex numbers, but for here we're dealing with real numbers, so you can't have a square root of a negative, and you can't have a 0 denominator. So knowing that, what we can do is then solve this equation here. So take the x squared to the other side, so you have that, okay, and then take the square root of 1, so get rid of that. But when you do that, you also take the negative square root as well, and that's when the sign flips over. So you have plus or minus the square root, and so that means that x has to be in between. It has to be less than 1, but it has to be greater than negative 1. So this particular derivative here is only applicable when x is between negative 1 and 1, not inclusive. So the key result, and I'll circle it in red, is our derivative for inverse sine, which is 1 on the square root of 1 minus x squared, provided x is between negative 1 and 1. And just looking back, just for where you're going, these are the 3 results here that you should know. Inverse sine, the one we just derived. Inverse cosine, you can see the difference is a negative sign, and that makes sense. Remember differentiating sine to cosine, there's that negative that gets involved when you're doing derivatives that way. So that's where that comes from. And inverse tan, the trick with this one is to link to sec, that link between tan and sec. These are the more general cases as well. So if you have x over a particular constant, or in any of these, the constant is squared here underneath the square root. So in these cases, this is the particular case where a equals 1. So the denominator for the x is 1. If the denominator for the angle x is not 1, then you've got this more general case. So they're your derivatives for inverses, and you'll also find that those particular derivatives are on your formula sheet. So both forms, the general case and the particular case where the denominator for x is 1.